Bismillah ar-Rahman ar-Rahim. This is some questions about primitive and integrals. So we suppose that f is a function defined on a closed and bounded interval AB, a part of R. We need to justify our answers about the following statements. So we have to say if they are true or false with argument. The first question, if f is a continuous function on a closed and bounded interval AB, so f admits a primitive on AB. This statement is true, and it is true because this is the fundamental theorem of calculus. So the fundamental theorem of calculus says that if we have a function which is continuous function on a closed and bounded interval, this is mandatory, necessary. So we define this function, then this function, which is the primitive, it is differentiable on AB, and the derivative of capital F is exactly the continuous F. To deal with this, so what we know, I'll be back. So for if each continuous function on a closed interval AB and bounded, so automatically f admits a primitive. So to deal with this statement, to give a proof. So actually, honestly, we are going to give a proof for a so famous theorem to justify this as a statement that are true. So we define this primitive, and we have to prove that the capital F verifies on each point AB, f prime of x equal to f of x. So we have that f is continuous on a closed interval AB. So it is uniformly continuous because we saw this in continuous function. All continuous function on a closed and bounded interval, in other words, in a compact interval, is actually uniformly continuous. It is uniformly continuous. This means that for each epsilon, there exists a delta. This delta depends on epsilon, such that for all t and x in AB, such that the absolute value of the difference between t and x, which are less than delta, and this delta does not depend on x and t. So we have the difference between the images is less than or equal to epsilon. We consider first that H is between delta and 0, which means that we are here. So this verify this inequality. Then for f of x plus h minus f of x, by definition and by relation on integral, we have that it is equal to this one. Then if we take f of x plus h minus f of x over h minus f of x, we can just write the difference between definition. So for this it is exactly this one. this one. And remark that the integral depends on t. Here it depends on x, f of x dt. We take f of x outside the integral, and if we calculate this, we will get exactly f of x. But this is less than or equal to n 1 over h, the integral between x and x plus h, the absolute value of the difference. And since this difference is less than epsilon, and the integral of dt from x to x plus h, the difference is h, and h over h is equal to 1. Which means what? Which means if we approaches x from the above, we will find that the difference is f of x, the limit, which means that f prime at any given x is f of x. We have to do the same thing with h, which is in the other side, which means that between minus delta and 0. So we have to do the same thing. We use the same techniques, which will give us f prime of x is equal to f of x for all the point. Why? Because at the right and at the left, we have the same value. The second question, or the second statement, we have here to pay attention, more attention. Why? Because for the first question, it is a classical one, it is well known. I just gave and show the proof of the fundamental theorem of calculus. Actually, the fundamental theorem of calculus is one of the famous theorems in calculus. For the second statement, if f is a function which admits primitive on AB, do this implies that f is continuous? Actually, this also is false. Why it is false? It is sufficient to give an example of a function which admits a primitive, but this function is not continuous. So if we define this function f of x, which is equal to x sine 1 over x minus cosine 1 over x, if x belongs to 0, the interval 0, 1, and is equal to 0 if x equal to 0. So for this function, we can prove that f of x, which is x squared sine 1 over x if x is in 0, 1, and 0 if x is 0, 1. This function is differentiable on 0, 1. And f prime of x is equal to f of x for each x in 0, 1, the half open or half closed interval 0, 0, 1. And using the definition of the differentiability at a point, we can show that this is equal to this, which is equal to 0. And here we use a kind of squeeze theorem. This means what? This means that f is differentiable on 0, 1 closed and bounded interval, and for all x in 0, 1 closed and bounded, f prime of x is equal to f of x. As a result, little f admit capital F as a primitive, but it is obvious that f is discontinuous on 0, 1. Why? Because it is discontinuous at x equal to 0, the little f. So we just verify here. Here we saw that we see that we have a jump at x equal to 0. Why? Because the limit when x approached 0 from the above, it is not well defined. So we cannot find the limit, and we can prove that f of x does not accept limits from above. The third statement, if f is continuous over AB, closed and bounded interval, then f is integrable over AB. This is true. Why this is true? This is true because since f is continuous on AB, so f is uniformly continuous on AB, the same reason as above. So if this is true, so for every epsilon which is greater than 0, we can find a delta which is greater than 0. Delta can depend on epsilon, but not at all on x and y. So if the difference is less than delta for each x and y in AB, we have f of x minus f of y less than epsilon over b minus a. And here we can take epsilon over b minus I by the mean of changing the epsilon, because epsilon over b minus I, we can take it epsilon prime, or we can take here epsilon prime, then we take epsilon prime over b minus I as epsilon. So we have this final result. We take a partition of the closed interval AB such that the partition is x0 until xn index 0. Uniform partition, uniform lengths between each successive points, and we will take them b minus I over n0 for n0 large, sufficiently large positive integer number. So this partition gives us subinterval relative to this partition, and we take m index e, the supremum of f of x on each subinterval, and this supremum is well defined. Why? Because we have a continuous function on a closed interval, and we know from calculus that there exists a point such that this is attained. We have the same thing with the infimum, and if we take the upper Riemann sum minus the lower Riemann sum, which is defined, the upper, it is defined so by ME, and this is the difference, and the lower is defined by the difference. If we take the difference between them, it will be exactly equal to this, but this actually is positive. Yeah, okay, because this is the maximum and this is the minimum on the same subinterval. So we can take the absolute value, it does not change anything. But here at this level, what we have this difference is less than or equal to epsilon over b minus I. So we cancel b minus I with b minus I. And here we have n0, since we do the sum n0 times, so we have here n0 on n0, they will be cancelled, and we will retain just epsilon. This, what does it mean? This means that we won to find a partition such that the difference between the upper and the lower sums are less than or equal to epsilon. And this is the characterization, the test Riemann integrability of f on AB, since it is well verified. So we can confirm that for any given function which is continuous over an interval, so f is integrable over this interval. The fourth statement, and we have to pay more attention here, if f is an integrable function over closed and bounded interval AB, so f is a continuous over this interval. This is not true. Why? Because we can give a counter example. So we consider the function f of x, which is equal to the integer parts of x on the interval -2, 1. So we know that f is integrable over -2, 1 in the sense of Riemann. Why? Because it is a piecewise continuous function over -2, 1. So it is a step function. But f is a discontinuous function over this closed interval, because simply f is discontinuous at x equal to -1 and x equal to 0. I recommend that someone can draw the graph of this function, and it will be obvious that it is discontinuous. This is not a proof, but just to feel more comfortable. The fifth statement, if f is integrable over AB, then f admits a primitive over AB. Unfortunately, this is not true. This is false. We can get a function which is integrable over AB, but f does not admit a primitive. To show this, we can take this function. It is the integral parts of x over x on 1, 3, for example. So we have to cancel for x equal to 0 to have a good function. F is integrable on 1, 3. Why? Because it is piecewise continuous over 1, 3. But f does not admit a primitive on 1, 3. And here we have to work a little bit to understand why. Why? Because your function, if you will take it, at a point, I think that at a point x equal to 2, our function, if we take a primitive, our function, the primitive does not admits a derivative, because it is from side 1/2 and from the other side is equal to 1. And since from side from the above it is equal to 1, and from the below it is equal to 1/2 at the point x equal to 2, which means that f does not admit a derivative at the point x equal to 2, which means that the little f does not accept a primitive. The last statement, if function f, which is defined on AB closed interval and B, if it admits a primitive, then f is integrable on AB. Unfortunately, this is not true also. So we can find function f which admits a primitive on an interval, but the function f is not integrable on this closed and bounded interval. To see clear, let us consider this function. So this is kind function, capital F, we can verify that this admits this one as a derivative, this, but. So this is the derivative, the derivative function of capital F. We can verify easily. If x belongs to 0, 1, we can take the derivative straightly. And we use the definition if x equal to 0. Then this function is not integrable. Why? It is not integrable because we say that a function f is integrable if it verifies two statements, two conditions. The first one, it have to be bounded. And secondly, if we take the infimum on all the upper Riemann sums, relative the infimum has to be taken over all the partition. This value must be equal to the supremum on all the lower Riemann sums. So we have two conditions, but the first condition must verify that the function is bounded. But here, the little f is not bounded when we approach 0. Why? This will explode. I finish. Thank you. See you next time.